Hey guys, this is my lab 4. This is oscillations. So for the introduction of this and our purpose is we were estimating the motion of a rope by treating it as a spring. In this lab, we will be using Newton's second law to predict the future motion using position and velocity. We will also be using the force of gravity in the negative y direction. And we will also be using the spring force formula because we are actually interacting with the spring and watching its motion. We will also be finding the stiffness by using periods of oscillation, and in this, T represents our period of oscillation. So if we go into our tracker and we analyze the video, you can see that the object is moving and oscillating, hence the red dots that are following it all the time. And if you look in the top right, you can see that it is oscillating up and down, up and down, up and down, tracking the motion of it in the X and Y direction and tracking the seconds of it. So now we had to find the spring stiffness, the relaxed length, and the periods of oscillation. Here, I just took a picture of what I actually did to compute it. I can walk through it real quickly. So we just said that K, our stiffness, was equal to 4 pi squared times the mass of our object over T, which stood for our periods of oscillation. We were already given mass, so all we had to do was just find T, which we did by looking at tracker, and we got 1.524 seconds for one period of oscillation. So then we just plugged that into our equation, and we got 6.833 newtons per meter. And then we also ended up using the equation of L naught equals L minus mg over K. So then we plugged that in and we ended up getting 0.1232 meters for our relaxed length. So now looking at our experimental data, we were already given the mass of our system. And once we found our relaxed spring length and our spring stiffness, we also realized that F net was equal to the force of gravity plus the force of the spring. Here, T is just equal to the periods of oscillation, and here's just a bigger picture of what we saw in tracker. Now for our coding, we had to change the mass of our ball. We also had to change the position vector. In this, we looked at tracker to obtain what our initial position was. Here, our initial velocity is going to be 0 because we are at the point where we're about to release it. So everything is still 0 up to this point. As we continue on with our coding, we also had to change our while loop, and we also had to change the energy changes as well along, such as our gravitational potential energy, our kinetic energy, and our spring potential energy. And this all works with the energy principle that we'll be looking at later on. We also use the momentum principle, hence Newton's second law, to update the position and formula as well. So once we go into GlowScript, we can see that once we plug in our CSV file and run it, that we have our change in energy versus time graph, which shows our gravitational potential energy, our spring potential energy, along with our kinetic energy and our total energy. And here, our total energy is this orange line, and it's 0. We also have our position versus time graph of the oscillations for our observed and what our predicted one should be, and this is for the Y data. So for what does it mean? Is the energy principle satisfied? Yes, I would say that it is satisfied. We're looking at this graph and we see that our gravitational potential and spring potential energy, they are the same size, but they're in different phases. As one is decreasing, the other is increasing. The kinetic energy also changes. It goes from increasing to decreasing, positive to negative. But most importantly, looking at our total energy, it is 0 across. And this satisfies the energy principle that the change in energy will always be 0. So for what does it mean? When we're examining our estimate from the X position and our estimate from the Y position, just by looking at the graphs, you can tell that the estimate from the Y position seems to be more in line and on track with what it really should be when we're observing the position of our spring and our mass. I would say the reason why this is so is because our Y position had a shorter oscillation time and an oscillation period. So just by looking at that, it would seem that it would be more on track with what our predicted one would be. Thank you very much.